I'm very excited to tell you a little bit about Odum's energy systems language, and then separately afterwards tell you about combinatorial species and network models, and then give a vague proposal of a way to connect these things together. So these are the things I'm going to tell you about versus the toolbox of picture modules. He calls them modules. Just little components that go into his picture language. And then I'll give you a couple of examples of converting like an actual system into a picture. And then I'll tell you about combinatorial species, which is well established. And then I'll tell you about network models, which is a newish thing. And then I'll tell you about my proposed connection. So this picture is supposed to be a picture to explain Odum's idea about a macroscope. So in this book he wrote called Environment, Power, and Society, in the introduction he talks about how Leeuwenhoek invented the microscope, and it opens up our ability to see our world at a different scale, and things that we had no conception of before, and in particular to look at things which collectively combine into things we can recognize. So cells, we can't see them, but then they work together and collectively create, humans and other things that we can recognize. And so the sort of inverse of that, or the looking in the other direction, is asking, are we components of something that when we combine, we become some bigger thing that we also can't see, but for like the opposite reason, sort of. And so it's pretty clear that the answer to that question is yes. There's society, and then there's like the ecosystem, the universe, I guess. And so it's important for our understanding of the world if we to look at this macroscope as well, to look through a macroscope and see a bigger picture than we're normally able to see. So this picture didn't come out so well, it's a screenshot, but it's a picture that was in there. So first I'll tell you about the toolbox, the collection of, this is some of the modules that he uses in his energy systems language. This one's called source. An example is the sun is a source of energy. Also, fossil fuels can be viewed as a source because if you limit your scope, then you don't really see anything going into fossil fuels. It's just a thing that we can access, and it provides energy. Also, water from a reservoir, so water that somehow got into a place a long time ago, and like I said, from a limited scope, it just looks like it's always been there. And I guess the sun also fits into that model. Somehow the stuff that is in the sun got there, but you limit your perspective, and the sun's just always there and always providing a bunch of energy. I rearranged the stuff that I'm going to tell you about from this picture into first the ones that I think are most easily seen as having a categorical analog. So the source is like an initial object. You need help?
Sorry, I'm just focusing.
Okay.
Yeah.
Great. So you can think of a source as like an initial object, probably. Odum says that when you're drawing out a system, and you have a source, you should include data about how the source is providing energy. So like the sun, it's probably constant, unless you're only looking at like one half of the Earth or smaller, then it's going to be in like a cyclic thing where the amount of energy you get from the sun is changing over time, and then there's a lot of other possibilities, and then square wave, sine wave is the one I mentioned about the sun, if it's constant or if it's constant in flux. These are all different. This is data that should come with the source when you draw it into the picture. So heat sink, you can't keep track of all energy, even though energy is conserved. You can't keep track of all of it, and a lot of it is lost to heat. And so the heat sink is the symbol that like looks like it comes directly from circuit diagrams, and this is a really important thing to keep in mind anytime you're making one of these pictures of a system using this language, because energy is lost in any real spontaneous process. So that's what that is, and this, like categorically, maybe this is like a terminal object. Okay, so then this one is called adding junction. So if you have two similar forms of energy and they're feeding into the same thing, then you can just add them. And it's called adding junction specifically because there's other ways of combining energy. This one's splitting, and so something to keep in mind with this one if you're trying to think categorically is that if we have like a co-multiplication is really like a consistent way of specifying how to split an object into two other objects, whereas this is really just like an informal splitting. So I mean splitting in like the natural sense, not like a co-multiplication or anything like that. So that's something important to keep in mind. Yeah, so that's what I meant by that.
Is splitting flow, is there a reason you use the word flow instead of energy, like in the previous slide? Is that important?
Like in the previous slide?
So in the previous slide you added energy.
Oh.
And now you're splitting flow, so are they like two different?
From what I was reading, it seems like he uses his analogies very liberally.
Mm-hmm.
And so sometimes he'll be talking about energy, and it's probably actually energy, but he could also be talking about like money. Like money is another thing that will come up. And then, I mean, are you calling money energy? I don't know, but the same like stuff is applying. So it's flow of something, and he calls it energy a lot because that's primarily what he's concerned with, but sometimes I guess the words just change. So so here I used flow. So interaction. So interaction is when, so here he called them forces, but really he means the same thing as what I've been talking about the whole time, which is energy or flow. And it's two forces are coming together and interacting in some way. And the interaction will have loss through heat, right? So that's why that's there. And this outward arrow is some new form of energy or something is flowing out of it because there's a productive interaction, produced something. So he said a person turning a valve, and originally I included this with the intention of asking the audience what you guys thought exactly were x1 and x2 in that situation. Actually, so I'll do that. So what are probably x1 and x2 if a person turning a valve is this?
Wrist torque and whatever, gas or water or whatever.
Right.
Valve is.
Yeah. Yeah, that seems like a reasonable guess. So x2, so he specified that the one coming through the top is supposed to be thought of as like an intervening force that like is necessary to cause this stuff to happen, whereas the X1 is, it sort of looks like it's flowing through this interaction, like into it and then back out of it. So that's the one that's supposed to be thought of as like the thing that's actually flowing, but really you're putting energy in through X2 as well. So X1 is probably, so you said gas flowing through a pipe. So X1 is probably gas flowing through a pipe, and then out is probably also gas, but the energy is needed to turn the valve to make this possible. And there's heat loss there through probably friction with the valve and the pipe or whatever, for example. Oh, there's another example. So the interaction of limiting fertilizer with sunlight and photosynthesis. So what are probably X1 and X2?
X2 would be sunlight, triggering photosynthesis maybe? Or no, I guess the other way around. The fertilizer is a catalyst or something?
Yeah, I think that makes sense because sort of, if, to make the analogy with this, the hand is limiting the gas by not turning on the valve or something. And then here, the fertilizer is limiting the photosynthesis by not like giving the proper nutrients to the, or giving only a certain amount of proper nutrients to the plant, so that limits how much it can take the sunlight and convert it into sugar. So miscellaneous box. It's just a box, and you can use it for whatever you want. So one-way valve, so whenever it has an arrow and then there's a line cutting it off, it means it only goes this way. So this is also kind of odd for string diagrams in category theory, where strings go in a certain direction, and if you want to go in the other direction, you have to put a different string that actually goes the other way or something like that. Whereas this is saying if you just drew an arrow, you're not really saying that it has to go this way, you're just saying I'm thinking of it as going this way, but it could go the other way, and I think that literally happens in electrical circuits. Electrons flow back and forth constantly, and then they just average one way overall.
Yeah, in a bunch of our work on electrical circuit diagrams, we put arrows on the edges, even though there aren't arrows on actual wires in an actual electrical circuit, because we and everyone else likes to talk about electrical current as a number, and so you say like 5 amps, that's an amount of current, but that doesn't tell you which way the current is flowing if you just say 5 amps. But if you drew a little arrow on your wire, you could adopt a convention that 5 amps means 5 amps flowing that way, and that's what they implicitly do in electrical engineering. And then negative 5 would be 5 amps of current flowing the other way. So it's very important that you can have negative numbers there to indicate that it's flowing in the other direction. And so there, the arrow is just meant to be like a method of converting something into a number. It's actually giving you an isomorphism between one-dimensional vector space and the space of numbers. Without picking the arrow, you wouldn't know the isomorphism. So it's fun to think about that stuff.
Right. I just wanted to check. Are the numbers counting down for the time?
Mm-hmm.
Okay. Just never. Oh. Yeah. So when it's this, it means that I think of it going this way, but who knows? This is saying no. It literally goes that way only. There could be another arrow that goes backwards, but it's saying this arrow only goes this way. So I could imagine that probably water flowing down a mountain due to gravity is probably pretty well described right now. Wait, did I skip something? Yeah, so I just put this back in to say that, I don't know.
Some of those, you're still describing.
Yeah, I'm still describing. I had written that there. So a cycling receptor, this one was a little odd to me, so I actually just put not the full description he gave, but a lot of it, so that anything I didn't really get could possibly be interpreted. Here there's an interaction, and sorry, the picture's not that great. Here there's an interaction, and then here there is something that I think I put out of order. So, did I not yet talk about storage?
No.
No. Okay. So I accidentally put this in the wrong order.
Maybe you never wanted to.
No, I wanted to talk about storage. I somehow just didn't. Okay, well then I'm gonna have to tell you from this picture. This one's called storage. It has a little roof on top of a circular part. And the idea is that stuff can go in and stuff can go out, but you're supposed to think of it as a place where stuff stays. That's pretty self-explanatory. Yeah, so this cycling receptor, there's an interaction, there's some flow coming in, and then there's a storage, and there's another storage where some interaction produces an output and then also puts something into this other storage which comes into here. So the example that I think makes sense to me is that this can be thought of as like a creature. This is the mouth or something, or this is the process of eating. And then this is food, and then this is the processing of the food, and then this is waste, but it also produces energy and like usable biological energy. And then the usable biological energy is fed into the process of eating, which could be seen as a whole bunch of stuff, including like finding the food. Maybe if this is a whole species, then this includes like finding a mate and reproducing, and then eating, and then like literally eating, literally processing the food. All of that goes into is energy, biological energy being fed back into this process to acquire the food. And there's heat lost in everything.
So now we're on to not fundamental boxes, but some important ways of combining.
Right. I think there's going to be other sort of fundamental ones. Yeah, there's other fundamental ones, but some of these are built up out of other ones. I think that's somewhat informal, the way that they're built up. I think there's probably other stuff involved that is not there, so it's not a definition. It's not saying the cycling receptor is defined to be an interaction, two storages in a miscellaneous box. It's just an informal thing, but that's the way it's thought of.
A lot for us to do.
Yeah. So producer, this was a little confusing to me why they were listed separately, but this is also like a creature. This is all that was said about it. Usually contains storages and interactions. So here's an interaction, two forces coming in, something being stored. That storage goes back into the process, the interaction of stuff coming in, and there's some kind of waste, there's some kind of heat.
What's that little arrow coming in from the top that wasn't even on the left? So it's sort of upsetting to me that
This
that
one?
arrow is on the right-hand side, and it's not on the left. Oh, so the one little one
couldn't-
coming
I
out
could-
is also not.
Yeah, I couldn't figure out why it was, I mean, this looks more like an interaction where there's a limiting process, something limiting how much of the sideways one that can come in.
Yeah, so when you say producer, I'm imagining something like plants growing and like take in sunlight, they build up more and more of a store of starch or something like that, which I imagine is being stored in that bin there.
Yeah, so I mean, maybe this is like a plant with the fertilizer, like I was saying before, and that this is the fertilizer limiting it. This is the sunlight coming in, and also the other. I mean, the fertilizer could probably include the water and carbon dioxide, and then the sunlight is coming in and being converted into this energy, which is also feeding into the ability of the plant to do this process, and it also has waste. That's slightly confusing though, because there's also something called a green producer, green plant producer right here. Looks pretty similar, but I'll talk about the consumer. here, which has the exact same, the right-hand side is exactly the same as the previous one, like topologically. See that? And this one, it's just like squished or unsquished.
What?
So he just like thinks about them differently, even though he's like drawing the same components in them. A little odd. But he did this for like decades, refining it over time. So it's not like it's, you know, he didn't know what he was doing or something. He knew what he was doing. It's just hard for probably a mathematician with a very strict guideline for the way they like things to work to interpret. So yeah, it has the same stuff, but this is being thought of as different. So it represents an interaction of two inputs and an autocatalytic coupling of storage that amplifies inflow. So the way I interpreted that was that if this is an animal, then eating like increases its ability to eat more somehow. So it seems like another of the same thing. Green plant producer. So this one has this hexagon, which I have the toolbox nearby. The hexagon is the consumer. It was that one that was defined a second ago. For some reason that's a hexagon, whereas the other ones weren't. So this green plant producer involves a consumer and some other interaction, some other cyclic receptor. So a photosynthetic cell is the example that he gives, and I think that's probably the motivation for that hexagon. I think maybe chlorophyll is hexagon shaped, not sure.
It has a hexagon. Yeah, it has a hexagon.
So that is a switch. So I think that's more easily understood in computer science mindset than a biological mindset, but
Joe.
Yeah.
I noticed that when you introduced the interaction, there were two things coming in and two things coming out.
Mm-hmm.
And I guess that whenever you introduce something, those things are fixed, but then you use the interaction with two things coming on top and one thing coming in. So whenever you define something, are we to think that there could be multiple?
Yeah.
So this is not like strictly defined the way we see it now.
Yeah.
Okay.
And I don't think almost anything is as strict or formal as we would like it to be. I think that's probably our job as mathematicians to strictify and formalize and all that.
So, so it's sort of like the arities of these operations are flexible. So you
Yeah.
just have lots of things coming in.
Yeah. And it's definitely the case in the examples. We'll see that happening. Lots of different stuff going into.
But now you have two things coming into, and I was wondering, like, why two? if I can put any number there, then why two?
I don't know why he used this for like his default picture of a switch.
Okay.
That is
Is is the switch triggered by the two inputs on top being equal? And if they're not equal, then it doesn't flow through or something.
Or
I'm sure it could be like that.
Or it could be that you're making me think of like flipping a switch up or down, so that those two arrows coming in from the top are like flip it up and flip it down.
Oh yeah, maybe. Maybe he's like drawing the.
Because he talks about a binary choice, so maybe those are like the two choices. But then you have to worry about what happens if you press both of them. Yeah.
Yeah, and I like also the valve, the hand turning the valve could be seen as a switch too. So I think a lot of this stuff is very like some things are overdetermined and that's So I'm pretty sure you could think of it in multiple ways, and he probably would have encouraged that. I read that when he would teach this stuff in like lectures or classes, he would tell the students to like draw diagrams of just like anything that they like. In particular, if you had like students that were humanities majors, then he'd tell them like, try to draw these kind of diagrams for what you study, and then like lots of really cool stuff would come out of that. I didn't find examples, but the thing I was reading said that they were really cool. I should try to find them. So it seems like a lot of informal applications of this stuff to a wide range of fields has already been done by like undergrads and stuff that we're just taking as class casually. So it'd be cool if those were findable and then formalizable and scriptified and all that stuff. So here's where money finally comes in. Show that like he really was trying to think about a lot of things at the same time, and that's really what I want to try to do with what I'm going to propose, is that like thinking about different types of things and their interaction is really an important component of this energy systems language. It's like money interacting with the other things that we've already defined are like called like green plant consumer or producer, and so we're already talking about some kind of interaction, some kind of potential interaction between plants and money, and it'll make more sense when we get to examples.
They're both green.
So like the solid line is like real stuff, and the money goes in the opposite direction and is exchanged for the real stuff. And the heat could be potentially ignored in this situation if the process of paying for something has a negligible amount of energy that's lost in it. So that handing someone $1 is like negligible heat. So if that's the process you're trying to represent, you could leave off the heat or put a 0%. So money being exchanged for real wealth, flow of energy, goods, and services. Money goes in the opposite direction of the real wealth. So this is, so here's the part where it says heat sink may be omitted if that transaction is small amount of heat. So constant gain amplifier. So this one is also a little weird, but when it says gain, it makes me think about guitars and audio stuff. So if sound is coming, some kind of digital signal is coming into something and then is getting amplified, then the thing coming through the side might be the signal, and then this thing on the top is what controls exactly how much the amplification is. And then the output is the amplified signal. But the top thing might be a very small amount of energy in its actual contribution.
Yeah, so the gain means like the factor by which you multiply the
Right.
signal.
So reproducing species inputs effort from the left, generating an output of 10 more offspring, random numbers. Active impedance. So active impedance, this symbol looks like a storage because it is supposed to be thought of as like storage, and then the stuff that's coming in, when it reaches a certain amount, there's an effect of like limiting how much more is allowed to pass through this symbol. So that sort of reminds me of a capacitor. That stuff flows into a capacitor, and then when it reaches a certain charge, then it says no more. Or it's more like stuff flows into the capacitor, so there's no stuff coming out, and when it reaches its charge, then stuff flows freely again. Is that right?
Sort of like capacitors are somewhat mysterious. I mean, not all that mysterious, but probably it's not good to
Yeah.
get
Okay.
into it now.
Yeah, I thought it might be like a capacitor, but it's been a while since I studied capacitors. So I'm just gonna put this again right here for quicker reference as I go back. Now here's an example. So here's an aquarium, and there's this photosynthetic production where sunlight is coming in, and then CO2 and water and other random minerals go through some kind of process that produces organic matter, which is going to be sugar, and then oxygen, and there's going to be heat lost. This stuff feeds into the organic matter, I mean the heat's lost, so the organic matter and the oxygen are going through animals instead of plants up here. Probably animals, and they're going to produce mineral elements, CO2 from breathing, and H2O. I don't know why H2O is not on both sides, probably overstrike. But there's also heat lost in that process. So this is probably a way that someone would write this stuff down if they weren't trying to draw diagrams like Odum. So here's one component of how Odum would draw this picture. So here we're not going to use like thin strings. There's these sort of fat strings where the thickness is supposed to represent the amount, vaguely, of how much is going in. So like for instance, a really fat line could split into multiple thinner lines. Could split into multiple thinner lines. And the amount, they're like each smaller in a way that sort of adds up to the larger amount. And so this is just the materials flowing through the, flowing around inside of the aquarium. There's just like a bunch of stuff all over the place. And then photo producers, so the plants probably, pick up that stuff, and they use it in this process P, which is photosynthesis. And they produce the organics and the oxygen, so the organics was the sugar. And then this process is the consumers eating that stuff or consuming it in some other way. And then that produces stuff that goes back just into the dispersed materials. So this is just stuff, whereas the next one is going to be energy.
So he was lumping together, so there are lots of different kinds of stuff.
Yeah,
before.
lots of,
So here he's just lumping them all in as stuff.
yeah.
Yeah.
Yeah, so it's, you know, how zoomed out you really want to be. You're zooming out to a level where it's just, there's stuff, and there's like sugar, there's plants and animals, and that's it.
Yeah.
That's what flows around those fours.
I mean,
So
so one great thing for us to try to do would be to try to like get a formalism, which you sort of almost can do, where you have like the ability to describe this very zoomed out rough picture, but then like also imagine a much more fine grained picture where stuff was divided into different types of chemicals, and then like have some kind of morphism between the fine grained picture and the coarse grained picture. One great thing about physics and chemistry is that mass is conserved. So like whatever kind of stuff you're talking about, it has mass. And you could have these arrows here just be like the amount of mass of stuff that's going through. You don't care what it is. But then sometimes you do care what it is, so you need some more fine-grained descriptions too.
It's a very Willems kind of approach. It's like zooming in.
Yeah,
That's
so
actually
Willems
literally the
came,
word they use.
yeah, so Willems came later, I think, and so now I'm really curious like how much Willems was influenced by this at all. But Willems was a much more quantitative guy. He was in a math department.
I was just going to say that Odum is a fan of like drawing stuff as being like black box version of more complicated stuff, as in the definitions I had shown previously, where you said this is equal to this, and so that's like you could look at one of these as having this stuff like inside of it. You just like draw a big thing around it.
Mhm.
So the
So he is a fan
algebra
of
of wiring
that.
diagrams is sort of perfect for that type of
Mhm. That's true.
thing, sticking a bunch of little boxes together and saying, okay, well, I'm gonna think of that all as a bigger box.
Mm.
So here's the energy perspective on the same system. So we have the sun coming in, and this is what I was saying before, where you have like a really fat flow of energy, and then some of it just goes elsewhere. No one knows where. But a lot of it goes into the photo producers, and they need that energy to do stuff. Some of this energy that they produce is lost, as it is from the consumers. But some of it also goes into this. And notice that this light is really fat compared to this very skinny one. And so a lot of energy is lost in just processing sunlight and turning it into sugar. That's a really big thing that you did to it. But it produces this stuff. A slightly thinner line is it being consumed by the consumers, and then a very thin line produces the materials that are necessary for this photosynthesis.
So this is a multi-layered language,
Yeah,
and does it also tell how to connect the layers?
yeah. So, I mean, tell how to might be. There might be like a gradient sort of answer to that. So that is exactly what I want to focus on. Is looking at this in a multi-layer kind of way, and then figure out how combining them will actually make sense. So here they are combined.
So here it looks like they've just been physically stacked.
Yeah, physically
each other.
stacked on each other, so cleverly arranged them.
Uh-huh.
Then you can just stack them on top of each other. And there's a lot of stuff that he goes into about taking this information that you've got and turning it into numbers, actually doing computations with it. And like he has a chapter on linear programming, so that when you have constraints on your materials, then like it, he talks about taking these pictures and then actually doing quantitative stuff with it. I'm going to skip that because I'm going to. It's in the book that you can read about.
Does he have like papers about that, or did he do any research?
I mean, he
about
has I didn't read any papers of his specifically. I read his book. I didn't read the entire thing, but I skimmed the entire thing. And then this is mostly from the chapter describing the picture language, because I think that's the main thing that we like want to get our hands on, and then we can, like, as a group or individually, go and find specific things that we want to do with it later. Like this is like just like the step one. Know what the pictures mean at all, and I think it names the chapters nice enough that if you wanted to find linear programming, just go to chapter 4 and it says linear programming, and you like go there and you can do computations if you want.
So I think one of his big things was developing a pretty detailed model of the Chesapeake Bay.
Mhm.
And it was a quantitative model in some ways, and he like went out and did a lot of measurements of things. And he also has like pictures of this type that are much more complicated. You would have like crabs and fish and all sorts of agents.
Right. Yeah, there's a ton of examples in the book. I'm just picking a couple random ones so that I can like make the point of separating it into certain perspectives and then figuring out how to realize them simultaneously. Sort of is what the approach is here. Like the idea behind it. Look at materials and energy as like separate, but then realize that they're not separate, they have an interaction. It's very important. That's the whole point. And then this is just rewriting the same thing, but with the thin strings, and you don't care about thickness representing amount anymore. And this looks more like string diagrams that we're used to, and that you're used to from when I was describing the toolbox. It's basically the same stuff. So photosynthesis is there. Sun produces a ton of energy, and some of it goes to the producers. Everything loses energy. Sugar's produced. Consumers eat it. And I don't know what that control is. I forgot to look at that.
You did have, that was the matter.
Oh,
feedback.
right, yeah. The matter feedback to the plants, that's true.
The last diagram, or the last, sorry, the one after
Oh,
this one.
after this.
Sorry, the last in that other sense. The last diagram makes me nervous because the wires are being used both for energy, some of them are for energy and others are for other things.
Right.
So you seem to not believe in typed wires.
No,
big
everything's very,
systems.
But did you feel relaxed about the thickness of them? Because that made me nervous earlier. The thickness of the energy coming in and less energy coming out.
I always think of that as just like how
Label?
I would think of that as just like you're using the thickness to describe a number labeling the wire, which is not really a characteristic of the wire so much as a characteristic of how much happens to be flowing through that wire in a given
Okay.
situation.
I see.
right.
Okay.
And the decrease in thickness should be seen as heat loss.
Mm-hmm. Okay.
It's just stuff that goes into the process.
I mean, we'll definitely want typed wires.
Yeah.
Yeah.
Yeah, so
So now that
he didn't know about type systems and computer science and stuff like that probably, so he wasn't thinking that way.
So erase that one. Now here's a new one. Just a completely different example now. So this is a house. Human residence means house, I guess. And there's things that come into it. There's wood for repairs. The house has to be maintained. There's groceries to feed the people. Then there's the pantry that stores the food. There's the people themselves inside the house. This dotted line is them breathing and producing CO2. Here's also a rat, which also lives in the house, also producing CO2. And there's a furnace, also producing CO2. There's gas flowing into a tank, storage of gas that flows into this furnace, which then burns it. That's producing the CO2, but it's also producing heat for the people to survive in cold times, I guess. Then there's termites eating away at the wood in the house.
Constantly being brought in to feed them.
Right. Wood for repairs is being brought in to counteract that force. And they're also producing CO2. And then here's a person leaving to go to work because it also takes money to get the groceries and the wood and the gas.
Oh, wow.
It makes
So-
it sound like the people's own role is to keep the house going.
Yes, that's what I thought.
Well, the house's role is to keep the people going.
Yeah, well, I know,
So they-
but
it's
here
a
like.
mutual relationship.
Yeah.
People live in houses, or do houses live in people?
Very
I
good.
think houses live on
Yeah, exactly.
or around.
Around.
So I put the toolbox here again so that I don't have to flip through 20 slides. So here is the string drawing of that house, just for the energy, or the materials section, sorry. So some of these strings didn't come out very well in the screen cap, but there is a line going this direction. You can see the dollar sign here. Money is coming out in exchange for the oil, I guess gas. I think some of this is slightly outdated, and I also don't know much about keeping your house warm because I live in a desert. But food is also going this way in exchange for money. Wood is going this way in exchange for money. Money is coming in exchange for this line, which is coming out of people. So people outputs this stuff that goes that way, and the other direction comes money.
Sounds like
That's-
you're selling the people, but.
Jobs.
The people go
Well, I
out
mean, the
when they
people
come
are
in.
selling themselves. by
Yeah, but they do
fractions.
come back in after they're done there.
Yeah.
Yeah,
There's a
but
feedback.
their time doesn't come back in.
Right, yeah.
That's what's really going out, is their time and energy.
Yeah.
Mm.
Uh-huh.
It's gone forever, but in comes money, that can be exchanged for wood, food, and oil. Then after those
The
things come
meaning
in,
of life.
after those things come in, they all have interactions.
Mhm.
Let's see, the wood has an interaction with the house. An interaction produces the
Like
house.
how rats are really important.
The house itself is like some amount of energy that's being stored. It's just like an analogy sort of, but the house itself is a resource that's being stored in this bubble. But the wood goes into a process which produces more of it. And it goes into this process which keeps the people alive. What else is coming in here? The people themselves have to put something into turning this wood into the house. So that's what this process is doing. Then this thing coming out of the bottom all feeds down to the heat sink. I think in, obviously that. So here's the food, it comes in, has an interaction with the people, of course. People come, interact with the food, and it produces stuff stored in the pantry. Stuff stored in the pantry contributes to people continuing to live. It also contributes to the rats continuing to live. And it also has heat loss. Let's see what else. I think this is the oil coming in. Yeah, this line right here is the oil coming in. The people have to interact with this oil to make it come in and be stored in the tank. But then that comes out and is burned by the furnace, but this line is also coming from the people, so the people have to do something to take oil out of the tank and put it into the furnace, which loses energy and also produces heat. So this is lost heat. This is like useful heat that keeps the people alive. The house also, besides keeping the people alive, it also keeps the termites alive, and they also lose heat. So I think,
Where'd the CO2 line go?
so that's not represented here. I think it'll be on the next one. But I don't think, we're thinking of CO2 as materials,
Oh, okay.
even though it is. And we're also thinking of heat as materials, so where the line is drawn is probably up to someone's choice. So here is another picture of the flow of carbon though. So the oil, the food, and the wood all have carbon in them, and this is supposed to represent the flow of the carbon only. So there's some process that was over here with some other input, but we're ignoring that input for now because it wasn't a carbon-based input. But the wood contains carbon, goes into the house, goes into the termites, produces CO2. I guess the house itself is not producing CO2, but the termites are. This also feeds into people, definitely producing CO2. Food goes into the pantry, and then the rats and the people both eat it, and they're producing CO2. So maybe the pantry's not producing CO2, but it's feeding the people and the rats. And the oil goes into the tank, goes into the furnace, out comes CO2. What?
Ooh,
I thought there was one more.
no
Okay.
more termites.
I guess that was those different things. We could combine them. It's not in here. Okay, so now I'm going to completely change what I'm talking about. I'm going to start talking about combinatorial species. Should I answer a question before I continue? Something about the Odum stuff.
Maybe later.
Okay.
I'd just be curious to for us to try out, like trying to
Yeah.
model something.
Yeah. Okay, so Andre Joel came up with combinatorial species, and here's a definition. Combinatorial species is a functor from the category of finite sets and bijections into set. So finite sets and bijections, if you think about the skeleton of that is going to be just natural numbers and then all bijections of a set of that many elements. And so this looks like the groups, the symmetric groups, thought of as categories, and then the coproduct of those. So just a bunch of symmetric groups sitting next to each other. And then you have a functor from that into set, then you have a family of sets indexed by natural numbers or indexed by finite sets, coming along with an action of the corresponding symmetric group on that. So that's sort of a weird thing on its surface, but the way you think about this is if you have a finite set X, F is assigning the set of structures, which are basically being described by F, that you can put on X. And it comes with a group action of the symmetric group of the size of that finite set. So here's an example. Simple graphs. So if your finite set is 1, 2, 3, 4, then here's two graphs, two different elements of the set simple of 4. And in particular, I want to say that these are two different ones because isomorphism classes are so important in graph theory that people often want to call these the same thing. Here, these are two separate things. Another example is another version of graphs, but this is directed multi-graphs, and so these are the ones that category theorists most like because they most look like categories themselves. And so for a finite set X, graph of X is the set of isomorphism classes of graphs with the vertex set X. And I say kinda because of the exact same thing I was pointing out here, that these two are different. And if you were thinking about the directed versions of these two things, those are going to be different also, even if they're isomorphic. What I meant by isomorphism classes is really that if you had this graph, where this is E and F, and then you have this graph, where this is G and H, I'm taking these to be isomorphic. And there's a very precise sense in which this is true, where these are isomorphic, but then this would not be isomorphic to either of these. Yeah.
So these are distinct, but there's an element of the symmetric group that switches 2 and 4.
Yeah.
Okay.
Yeah, there's an element of the symmetric group, which would make, yeah, so that isomorphism is not the isomorphisms that we're taking isomorphism classes with respect to. All this is figured out nicely in monoidal Wirthin deconstruction. Basically, I'm taking isomorphism classes here in the fibers of the fibration of graph over set. So that's what that means. Oh, and I guess I should say that the group action on all of these is permuting the vertices. I guess you said that. I didn't say it. So I'm going to give you some operations on them. There's other stuff that you usually do with species. I'm going to skip over that entirely because I think the operations that you can do with species are things that feel like stuff you should want to try to do with networks being described by Odum's language. We're taking, in both of the examples we took two different perspectives on a system, and we like smushed them together. And that's what we're trying to do. So I'll just describe a few operations you can do on species. And so this one, where you take two species and you take the disjoint union of the set of structures that can be put on the set X, the set of F structures and the set of G structures. The resulting species is the species that describes putting either an F structure on the set X or a G structure on the set X. So that can be used to combine species in this particular way, where you just are saying or. So you could, with the two examples I gave, directed multigraphs and simple graphs, you could put an F plus G structure on the set 4 would be, it's either a simple graph or it's a directed multigraph. And all of those, you're counting them together. Then this one, I just skipped to calling it day convolution because I didn't know whether to call it the product or some other kind of product. But it is the day convolution. So again, if I'm starting with F and G being the two examples that I gave, and I'm starting with a 5-element set, then one element of F O times G of 5 would be that I choose some subset of this and put an F structure on that. So I'm going to say, So I'm going to say that my first set is going to be this, this, and this. And then the second one will be the black points. And then I'm going to put an F structure on the blue points. And so that's going to be a simple graph. And I'm going to put a directed multigraph structure on the other partition. So that's something that could be described by this day convolution. You just chunk it up into 2 parts and then put one of the stuff on one part and something of the other stuff on the other part.
All possible chunks and including.
Yeah, I mean, you can, any possible division of it into 2 pieces, it would be legal. And then you just put stuff on those 2 pieces. And so it looks a lot more complicated when you read the definition because it takes into account what you just said, and then it like combines them all together because it wants the set of everything that looks like this. But that's a lot of things. So here's another product. And I didn't see this described explicitly where I was reading, but it seems pretty obvious, and it also seems pretty useful. So just tell you what it is. You just take the product of structures on the set, of F structures on the set, and the G structures on the set. And so what do you get? You have, let's say it was 5. That means that you have a simple graph on 5 elements, and you have a directed multigraph on 5 elements. So you can think of it as just the same, it is the same set. You don't have to think of them as separate. So you just have a simple graph on it, and then you just also have a directed multigraph. Okay. So you're just like putting multiple structures on the same thing. Now you're saying, this is my new structure. It's putting both of these structures on it at the same time. So that produces a new thing. This one in particular, I think, looks very, like maybe the thing that we want to look at if we're trying to describe what we were talking about a second ago, where you have different like subsystems in the same system, like different slices of the same system, where here I'm only looking at carbon flow, here I'm only looking at energy flow, this is material flow. They're all different things, but they're on the same set, right? And so we're taking different types of networks and we're like overlaying them on top of the same set. So I think this one in particular looks like what we want to look at. We want to describe that stuff. I really wanted to. Yeah, just put a structure of each type on the one set. And then there's a bunch of other ones that I didn't bother to describe because this is the one I really wanted to talk about. And the other two seemed like enough to talk a lot about building up stuff out of simpler things. But John Baez and James Dolan call it inner product, and it's also, I guess, normally called Hadamard product. Then there's the Cauchy product, and then plethism is particularly interesting, where instead of going from finite sets and bijections to set in general, you go to fin set, and then you also don't worry about the other functions, and it's just back to finite sets and bijections. And if you have something like this, and you have another one, then instead of drawing it this way, you could have just written it this way, and then you have two things that you can compose, and that gives you a new one of that. So that wouldn't work out well for this, because there are infinitely many directed multigraphs you can put on any non-empty set of vertices. But this one would work well in that situation because there is a finite number of simple graphs. So that was combinatorial species, and now I'll tell you about network models, which is a thing that I've been working on for a little while. And it's going to be extremely similar to combinatorial species, but I didn't know about combinatorial species when I made up this definition, so it's nice to know that it's connected to something that other people have thought about. So here's the definition. Network model is a lax symmetric monoidal functor from S, which S is the skeleton of finite sets and bijections I was describing before. So it's an equivalent category. You could write fin-bij there if you wanted, and it would be perfectly fine. But now I'm considering coproduct, I'm considering disjoint union as a monoidal structure on that category. And I didn't want to call it coproduct just now, because it's not a coproduct in the categorical sense. It's just a monoidal product. And then instead of just set, I'm going into sets with a monoidal structure on them, and that's being made monoidal under the actual product, not some fake thing like over here. And so we're taking lax symmetric monoidal functors from there to there and calling them network models. That's a little weird until we look at examples. And so it's going to be very similar. Network models, what we use them for is to construct an operad where the things that are being described by this functor, the graphs, for example, they become operations in an operad. Then we do stuff with that. But it makes more sense with examples. So with the simple graphs, it is actually a network model where what this picture is describing is the monoidal structure on simple of 4. Yeah, so this is the monoidal structure this is the monoid structure on simple of 4. So graphs with 4 vertices, that gives you a monoid under this thing that I called union, and I think of it as overlay. It just says line them up, overlay them. There's only one edge here because that's a rule about simple graphs. So those are all monoids. And this, I think I already convinced you before, or at least I described it, how this was a functor. And now I'm saying that the laxator is disjoint union. So what that means is that if you have simple of n and simple of m, then disjoint union takes those and produces a simple of n plus n. Simple graph on the vertices, the disjoint union of the vertices. Right? And it forms a laxator, makes this a lax monoidal functor. I think a lot of, okay, that says thank you, but I didn't, the next part is verbal only. I think a lot of combinatorial species are actually monoidal in this way secretly, because a lot of it is just like stuff, and it's stuff that if you like take two of them and you just like set them next to each other, that's a new one of that stuff. And due to the like stuff we built up in the monoidal growth and deconstruction paper, that it's like very often I could imagine all those things being like co-products in some kind of weird category, and that always turns into a monoidal structure on the fiber. This is actually co-product in the fiber, and then here's a co-product, and then this laxator. It all just like comes naturally. It falls right out of the theory. So I think a lot of combinatorial species are actually network models secretly, and I want to figure out which ones are. That'd be really cool. But to connect this to the Odum stuff, well, I guess I've sort of been connecting it slowly over time. It seems like there's a lot of cool things where overlay is necessary to describe what's really going on by slicing up your system into a bunch of different perspectives and then recombining them. It's going to require some kind of overlay. And that's exactly what network models are really good at describing. In a way that like combinatorial species doesn't have enough structure to. Like the overlay is really the monoidal structure, the monoid structure on these fibers. And that stuff is completely ignored by combinatorial species. And all those products that I mentioned for combinatorial species, I think that a lot of them should be definable on network models, like exactly the same almost. They'll probably all work out, but we just never did that, so that needs to be done. And if we do that, then we can probably really nicely talk about combining networks in a way that, you know, describes what Odum's trying to talk about, but like in our categorical language. Okay.
Does anyone have any questions? So I guess at some point we'll have like tomorrow, maybe we'll have start a conversation where we try to like do it, where we try to take Odum's ideas and make them more mathematical. That's, I guess, one of the main things I want to talk about in this seminar next quarter.
Mm-hmm.
So we don't really need to start doing that right now.
Mm-hmm.
But if there are, if you want, you can. But if there are other questions or things to say, that would be. I'm a little scared of some questions because okay, so how do you create a monoidal category that contains termites and
houses,
rats and
yes.
houses? But we will figure it out.
Mm-hmm.
Yes.
So, as you started studying this, did you get any feeling that there might be some kind of presentation by generators and relations hiding in there?
I mean, it certainly feels that way, especially the way that he presents it is sort of the way that I present it, where it's like, here's a bunch of things, and you can combine them however you want, as long as like the strings line up, and you know, when you split things, it has to add up to what it came from, and when you combine things, it has to add up to that. So that all feels very generators and relations.
I feel like
Brandon
given a
and
bunch
I
of
were
stuff and
just-
given a bunch of rules.
I feel like you never mentioned the relations.
Yeah, I think the relations part is probably very situational. I think it's largely probably free, where it's just like you combine them like all kinds of different ways. If you want to be like extremely general about what you're describing, like it can describe like almost anything. You're just talking about stuff moving around, so that's a lot of things. like rules about what things are allowed to combine and what happens when you combine them, especially if one thing is being defined as a combination of other things. That is a relation. Rules about what's allowed to combine that aren't already present. That's actually information that should be in the generators, I think, like typing the wires
Types
and
of
stuff.
So, yeah, so Brandon and I did a bunch of stuff on props that were described by generators and relations. And all these things can be still thought of in that framework too. I think at least a lot of them. And so the diagrams that people draw are usually morphisms in props that are free without relations. So, and that's really good because what you want to use those diagrams for is you want to use them as ways of describing situations. And then if you want to know what actually happens in those situations, you want something like a symmetric monoidal functor from your prop to some other category, which describes semantics as the meaning of what you're drawing. And the best kind of things to map out of are free structures. It means that you can just freely map any generator to whatever the heck you want, and you don't have to worry about checking the relations. So syntactic categories tend to be free, and as long as you're just worrying about what kind of diagrams you can draw, then then the fewer relations you have, the better. But when you're trying to figure out what things mean, then that's where relations become very important. Like in me, if I have a 5 ohm resistor and a 6 ohm resistor, and I stick them next to together, that does the same thing as an 11 ohm resistor. And that would happen over in the semantics. So yeah, there's lots to do there. Okay, great.